Um, okay, so I'm going to start recording before the talk starts this time. So our second speaker is Polly Ann Jeffrey from the University of Leeds, and Polly will be talking for about 25 minutes on exact and approximate approaches for stochastic receptor-ligand competition dynamics. Polly, when you're ready.
Thank you. Yes, so my name's Polly. Thank you, Matt and Martin, for inviting me to speak today. I'm part of the mathematical biology group at the University of Leeds, supervised by Martin, Grant and Carmen. And my PhD is funded by the UPSRC and coordinated by the Smith Institute, and I have an industrial partner who are AstraZeneca. So today I'm going to talk about competition in the context of biological processes. So in the picture on the screen, I'm showing the surface of a cell, this pink line here, and everything below the pink line is the intracellular domain, and everything above the pink line is the extracellular domain. And the black shape on the surface of the cell is supposed to represent a receptor molecule. These are molecules which can interact with other molecules in the extracellular domain and with molecules in the intracellular domain. And when they do so, they can bind with these ligands in the extracellular domain, and we assume that these reactions are reversible. And this is important because you can have a lot of different receptor molecules on the surface of a cell, and when you form enough ligand-bound receptors, which we'll call monomers, this can induce a sort of cascade of events within the cell, which we call phosphorylation events. And ultimately, this leads to some fate for the cell. So dependent on the receptor type and the ligand type, this determines what the fate of the cell will be, where by fate we could mean something like differentiation of the cell, so the cell splitting into two, migration of the cell, or even death of the cell. And so I've said there's an element of natural competition because sometimes on the surface of one cell we can have multiple different types of receptor. So that's what I'm kind of showing there by the receptor on the right with a little cross over its tail. So that's not meant to mean anything biologically, the little cross, it's just to sort of distinguish it from the other receptor. So that could be a totally different type of receptor, or it could be, say, a mutant version of the first receptor. These mutant varieties are important in the context of disease, whereby in some diseases, such as some types of cancer, if you have a mutant variety of one of the receptors, it can mean that without binding to the ligand in the extracellular domain, we can already induce the cascade of intracellular events. So for example, we could have a mutant type of receptor, which could lead to division of the cell much more quickly. And that can lead to things like tumor growth. So that's why it's kind of important to study these interactions between the receptors and the ligands. And in particular in this talk, we're going to focus just on the interaction between the receptor and the ligand and nothing else intracellularly. So we can set this up as a stochastic model where I'm going to call the receptor of type 1 R1 and the common ligand L. And a receptor and a ligand can bind with a rate constant Kf1 to form a monomer of type 1. And like I said, these reactions are usually reversible. So with rate Kr1, that monomer can split back up again into the receptor and the ligand. And then we can introduce a second type of receptor into the model called R2. And R2 can bind with the same ligand with potentially a different rate constant to form a monomer of type 2. And similarly, these monomers can also dissociate back into the receptor and ligand. So these are the only 5 molecules that I'm considering in the model. We're assuming that the timescales are kind of short enough that we don't need to consider anything like synthesis or degradation of any of the molecules, and we're not considering internalization into the cell either. And therefore we can write these equations, which we call conservation equations. So NR1 can be thought of as the total number of receptors of type 1 in the system. And at any time t, that's going to be equal to the total number of receptors of type 1 plus the total number of monomers of type 1. And we can write a similar equation for the receptors of type 2. And for the total number of ligands, which we call NL, that's going to be equal at any time to the total number of free ligands plus the total number of monomers of type 1 plus the total number of monomers of type 2. And we can rearrange these equations very easily to obtain expressions for R1, R2, and L in terms of these fixed numbers of molecules, NR1, NR2, and NL, and the monomer types, M1 and M2. So in that way, we can reduce the dimensionality of the problem from 4 variables down to 2. So we only need to keep track of M1 and M2, and we then know everything about the process, provided we know these 3 fixed numbers. So in that way, we can describe the system by a continuous time Markov process, which we'll call curly X. And if we impose the conditions that the total number of monomers at any time t greater than 0 have to be greater than 0, because they're numbers of molecules, then we find that X is defined over this state space S of X. So a state is a pair M1, M2, little m1, little m2, where these are the numbers of molecules of type 1 and type 2 monomers. They can take any value in the natural numbers, including 0. And they're subject to these conditions where the number of monomers of type 1 always has to be less than or equal to the total number of receptors of type 1, and the same for type 2. And the total number of monomers of type 1 and 2, the sum of those totals, always has to be less than the number of ligands that you have in the system, less than or equal to. Okay, so we can look into the model then in a bit more detail by looking at the transition diagram. So in the middle of the diagram, we've got any general state in the process M1, M2. So this is the number of molecules of type 1, M1, and type 2, M2. And from that state in the middle, in a very small unit of time, we can go to one of 4 possible other states. So we can go firstly to a state on the right here, where we've increased the number of monomers of type 1 by 1, and M2 has stayed the same. So this is a formation of a monomer of type 1. And we can write down the rate at which this reaction occurs. So I've assumed that we're using mass action kinetics here. So mass action kinetics says that the rate of a reaction should be proportional to the concentration of the reactants. So we've got this rate happening with the constant Kf1 that we defined before, multiplying nr1 minus m1, which is equal to R1, the total number of free receptors of type 1, and multiplying NL minus M1 minus M2, which is equal to L, the total number of free ligands. So that's Kf1 multiplying R multiplying L. So they're the concentrations of those 2 reactants. Similarly, we could move to the left, so we could have a dissociation event of a monomer of type 1, and go with rate Kr1, and that's proportional to the number of monomers of type 1 that we have at that time. And then the system is symmetric, so we can have the same thing happening for the formation of a monomer of type 2 moving upwards, and a dissociation of a monomer of type 2. So this is a kind of stochastic process that we can simulate using the Gillespie algorithm, which is what I've done in the figure here. So on the x-axis, I've got the time in minutes, and on the y-axis, the number of molecules. And the solid green line is representing the number of monomers of type 1, and the dotted blue line is the number of monomers of type 2. So I've done this for 3 different situations where those parameter values are seen in the table at the bottom. So in the first case, situation A, I've kept the rate constants between the monomers of type 1 and type 2 the same. So the rate of formation Kf1 is equal to the rate of formation Kf2. But the number of molecules are different. So I started with 100 molecules of receptors of type 2 and only 50 of type 1. And that's why we see that in later times we end up with more monomers of type 2 than type 1, as we would expect. For case B, we've got identical number of molecules and identical rate constants, which leads to this kind of overlapping of the stochastic processes here. So this is a stochastic process, so there's some fluctuation here, which is why they're not just completely overlapping, but we can see that they're kind of taking similar values. And finally, in case C, we're keeping the numbers of molecules the same, but differing the rate constants. So the monomers of type 1 form with a faster rate than the monomers of type 2. And hence we see we end up with a lot more of the monomers of type 1 than type 2. So one interesting thing we can observe is that fairly early on, we seem to approach kind of stationarity in each 3 cases. So what we were interested in was if we could find the steady state distribution for the number of monomers of each type. So the steady state distribution will encode how many of each monomer type we can expect to see in the long run, so as time tends to positive infinity. We can write that mathematically like this. So pi m1 m2 is the steady state probability for a state m1 m2, and it's the limit as time tends to infinity of the probability that the process takes that state. And we have a steady state probability for every state in the state space. So I'm going to present an analytic approach to solving these steady state probabilities and a kind of novel approximation that we've come up with. So analytically, we can write the steady state probabilities in a row vector like this for all the states in the state space. And from the theory of Markov processes, these are 2 well-known equations which this system is known to satisfy. So the steady state probability is multiplying this matrix Q, which is called the infinitesimal generator matrix, which is essentially a matrix containing all of the rate constants, well, all of the rates from moving from one state to another. So those 2 things should multiply to give you a vector of zeros, and pi, so the steady state vector multiplying a vector of 1 should equal 1. So that's just a kind of normalization reaction. That's just to say that those probabilities should sum to 1. And those equations can be solved efficiently if we organize the matrix in a certain way. So by sort of organizing the states in the state space in a certain way, we can write the matrix Q in this block diagonal form, where each one of these Q00, Q10, these are all matrices in themselves, but the total infinitesimal generator becomes block diagonal like this, where capital N2 is just the minimum of the number of receptors of type 2 and the number of ligands. So I'm not going to say much more about how we can then solve this, but essentially we can use a matrix algorithm based on linear level reduction, and we can solve for those steady states computationally. So that approach works well when we've got a small state space, because solving those equations requires sort of inverting matrices, which when the matrices become large, which corresponds to the state space becoming large, which in turn corresponds to having large values for NR1, NR2, and NL, then the computation time can be very slow. So we can end up with, when those numbers of molecules reach just like several hundreds, the computational time becomes very slow. So we sought to try and find an approximation to this, which would work when we had a larger state space. So we noticed that the only thing that related the 2 monomer types was the common ligand. And therefore, if we had an excess of ligands, so if NL tended to infinity, then the variables M1 and M2 become effectively independent of each other. And that's because there's sort of no competition then. If we have just, if NL outweighs NR1 and NR2, then there's effectively no competition between the receptors on the surface for the ligand. So in this situation, we can approximate the 2D process using 2 one-dimensional processes, which we call X1 and X2, for the monomers M1 and M2, and they're defined over these state spaces. S of X1, say, is just the set of the number of monomers of type 1, which can take values again in the natural numbers, where M1 has to be less than or equal to capital N1, which is the minimum of the number of receptors and the number of ligands. So we noticed that these 2 one-dimensional processes are just birth and death processes, whereby from any state M1, say, we can only move up a state to M1 plus 1, so a monomer formation, or we can move down a state to M1 minus 1, so a dissociation event. And the rates at which these reactions happen are lambda M1, say, which is KF1, multiplying, so the term in brackets is NR1 minus M1, which is the number of free receptors of type 1. And I mean, technically we should have an NL minus M1 here to represent the total number of free ligands, but given that NL is tending to infinity in this case, we can just approximate that by just NL. And the reverse rate constant is the same as how it was in the two-dimensional process. So from the theory of Markov chains, in particular for birth and death processes, there are sort of well-known ways that you can write down the steady state probabilities for the 1D birth and death processes, and they turn out to be like this. So pi m1, say, you might notice there's a binomial distribution with parameters n equal to nr1 and p, the term in the first bracket here. And we can write a similar thing for pi m2. And then we can say that in the limit as NL tends to infinity, so when NL is very, very large compared to the number of receptors, we can get a good approximation to the 2D steady state distribution by just taking the cross product of the two one-dimensional distributions. And we notice that as well, because of that nice property of the binomial distributions, we can easily write down the expected number of monomers of each type in the steady state, which is just NP, or NR1 multiplying this term in the first bracket. So we get these nice expressions for the expected number of monomers. So this is all fine for values of NL that are very large in comparison to NR1 and NR2. We expect this approach to work very well. But we then sought to find an approximation that will work well also when NL is actually comparable to NR1 plus NR2, so for smaller values of NL. And what we thought we could do was use this same approach, so use these two one-dimensional distributions, take the cross product of their stationary distributions, but where we compute these stationary distributions using a value of NL called NL star, which we called sort of an effective number of ligands, such that that value is smaller than NL. And in that way, that's kind of accounting for some of the competition from the competing Markov chains by saying, like, instead of starting with the total number of ligands, we're going to start with a lesser value so that we end up with smaller values in the steady state, and that corresponds to some competition being taken into account. So this is then how we propose to come up with that value NL star. So essentially what we've done is we've come up with a sort of algorithmic approach to calculating the total number of ligands that we should use. So in the first step, we set capital NLI just equal to the total number of ligands in the original two-dimensional system. We then compute the expected numbers of monomers of type 1 and type 2 in the steady state from the two one-dimensional distributions using NLI. And then we do this sort of iterative scheme until we converge at a different value of NLI. So we pick a small threshold value epsilon, much smaller than 1, and then we say, while the expected numbers of monomers of type 1 and type 2 in two successive iterations are greater than that value of epsilon, we start by taking the total number of ligands and subtracting the expected numbers of monomers of each type in steady state. And that'll lead to a much smaller value of NL. So for NL2, say, we also we multiply by a value alpha and a 1 minus alpha here and take some of the last value of NL. This is just because in some cases you could have NL minus these two expected values becoming negative, which we don't want to happen. So this is just to kind of keep those values positive at all times. So then once we've got this new value of NLI, we then compute the expected numbers of monomers of each type again, and go back through the process again, see if they're close enough to each other, and if they're not, then we subtract the expected numbers of values using the new value of NLI. And basically what we find is that we start with a high value of NL, and then we kind of oscillate and end up converging to a value of NLI. And it turns out that when we use this value of NLI to then compute the steady state probabilities for the two one-dimensional processes and take the cross product, and then in line 10 there we're just normalizing to get proper probabilities there, we end up with a very good approximation in a lot of cases to the two-dimensional distribution. So we called our distribution here pi MCA, which stands for moderate competition approximation. So here's how they compare for one particular set of parameter values. So on the left, we've got the exact matrix approach, so that's the exact approach, and on the right, we've got our moderate competition approximation. And then the two rows correspond to different numbers of ligands. So in the top row, we've only got 100 ligands, and in both cases, we've got 100 receptors of each type. And in the bottom case, we've got 500 ligands. So we see in the bottom case that the two distributions, so each pixel here represents a state in the process, so a number of monomers of type 1 and type 2, and the color represents its probability. So the kind of whiter the color, the higher the probability. So these are kind of heat maps of the distributions. So we see in the bottom case that they're almost identical, and the expected number of molecules of monomers of each type from each of the two approaches is also almost identical. When we decrease the number of ligands and we go to the top row, we see that the shape of the distributions isn't approximated very well by the moderate competition approximation, but we still do capture the expected number of monomers of each type in steady state quite well. So to sort of, we then did a kind of thorough numerical comparison to see where this approximation worked best. And essentially what we've done, so we've computed the Hellinger distance, which is a measure of the difference between two probability distributions. It takes values between 0 and 1, where 0 indicates that the distributions are identical and 1 that they're completely different. We took three different values of NL, the rate constants. We sampled from uniform distributions, and what we've plotted on the right, the x and the y axes, are these things that we've called competition parameters, where basically the higher the value of NR1 over KD1, where KD1 is the ratio between the on and off rate constants. So the higher that value, the more the competition for the ligand, and the lower the less the competition for ligand. So what we see is that in the case where we've got NL low at 100, and these competition parameters are very high, we end up with high values of the Hellinger distance. So in this kind of region of the parameter space, the approximation doesn't work so well. But even for such a low number of ligands, when we get to low competition regions, the approximation works very well. The Hellinger distance is much less than 0.1 in this bottom left corner. So this kind of corresponds to events where you've got very slow rates of binding of the receptors to the ligand. And then as we increase NL, so we increase the number of ligands in the system, the approximation gets much better. And by the time we've got 500 ligands compared with up to 200 receptors of each type, the approximation works very well everywhere in the parameter space. So just to conclude, we've been able to compute the exact steady state distribution analytically for a 2D process when we've got a relatively small state space. But when the state space starts to increase, this approach becomes computationally infeasible. So we've developed this approximation to use instead. The approximation would be easy to extend to higher dimensions, so we could add a third or fourth receptor type, whereas the analytic approach would be much more difficult to do that, both in terms of writing down the matrix forms, and it would increase the computational intensity again. We found that our approximation works best in the regions of parameter space where there's low competition, and we think that we can use this kind of approach of using two 1D processes to approximate a 2D process for other summary statistics and for other areas outside of mathematical biology. And there's a few of the references we use. So Reuter was the first person to come up with these kind of stochastic competition processes. Eaglehart generalized some of those methods. There's a book there about matrix methods, and then the fourth one is a paper that we published last year on these approaches. And I should say thank you as well to Mario Castro, who also helped a lot with this work. So yeah, that's it. Thank you very much for listening. I'm happy to take any questions.